Welcome to The Explainer. I am absolutely thrilled to have you here today. As financial analysts and investors, we are constantly faced with this massive, seemingly impossible problem. We need to make highly accurate conclusions about incredibly vast populations of data. But we're all universally constrained by two very real, very stubborn limits: time and money. We literally can't look at every single data point. It's just not going to happen. So, how do we solve this? Well, we open up the Data Detectives Toolkit, which is all about estimation and inference. Okay, let's dive right into this and check out the tools that are going to empower us to eliminate bias and extract real precision from total chaos.
So, here is our roadmap for today. We'll be looking at the power of sampling, probability sampling methods, non-probability sampling methods, the Central Limit Theorem, and finally, modern resampling techniques. Section 1. The power of sampling, trading time and money for error. Imagine for a second that you're a wireless equipment analyst. You desperately need to know exactly how much major customers are going to spend on equipment during the coming year. Ideally, you want the exact population mean. Now, one strategy is to survey every single wireless equipment customer in existence, the whole shebang. But let's be real. Pulling the entire population would be incredibly costly, right? There is nowhere you have the time, and you certainly don't have the budget for that. So instead, what do? You collect a representative sample. You compute the sample mean, and you save a massive amount of time and money. But that savings definitely comes with a catch.
And that catch is sampling error. You can think of this as the inevitable villain of our story. Whenever we decide to only look at a subset of data rather than the whole population, we're introducing error. It's literally the exact difference between the statistic we observe in our sample and the true population parameter we actually want to estimate. When an analyst chooses to sample, they are actively trading time and money for sampling error. Now, our goal here isn't to pretend this error doesn't exist. Actually, scratch that. We know it exists. Our real goal is to manage and minimize it using the right sampling plan.
Moving on to Section 2. Probability sampling methods, eliminating bias. To set the stage here, we really have to contrast the two major approaches to drawing a sample. First up, probability sampling. This gives every single member of the population an equal chance of being selected. It is mathematically objective, and it creates a truly representative sample. On the other side of the coin, we have non-probability sampling, which relies entirely on a researcher's judgment or just pure convenience. Now, all else being equal, probability sampling is going to yield far more accuracy and reliability. So let's look at the specific probability tools we actually have at our disposal.
The absolute most basic tool in the box is simple random sampling. It's exactly like our wireless equipment analyst randomly pulling company names from a hat to poll. This method works beautifully when your population data is homogeneous, meaning the characteristics of the data are all broadly similar. But what if your population isn't uniform? What if it's incredibly complex and diverse?
Well, that is where stratified random sampling comes in, and it's a real game changer. It's incredibly useful. You take your complex population and divide it into subpopulations, which we call strata, based on specific classification criteria. Then you just draw simple random samples from each stratum proportional to its size in the entire population. Doing it this way absolutely guarantees that specific subgroups of interest are mathematically represented in your sample. And as an awesome bonus, it produces estimates with much greater precision and smaller variance than you'd get from simple random sampling alone.
Let's ground this with a real-world application, pure bond indexing. Say you want to replicate the Bloomberg Barclays U.S. government/credit index. It contains thousands of illiquid issues, so buying every single one is literally impossible. If you used a simple random sample, you might accidentally pull bonds that completely miss the index's interest rate sensitivity. So instead, you use stratified sampling. You divide the index bonds by duration, sector, and credit quality into distinct cells. Then you pull a proportional sample from each of those cells. Boom! You've now accurately mirrored the index's risk factors without taking on those massive transaction costs.
Let's see how this concept builds into cluster sampling. This is your go-to when you have a vast population and you need the absolute most time and cost-efficient method possible. Here, you divide the population into mini representations called clusters. A great example is a broad market survey. Let's say you want to know if U.S. individual investors are bullish or bearish. Obviously, you can't poll everyone, so you group the population by state, treating each state as a cluster. You randomly select a few of those states, and then you randomly poll investors just within those specific states. It saves a tremendous amount of time, even though it might yield slightly lower accuracy compared to stratified sampling.
Section 3. Non-probability sampling methods, speed and judgment. As we established earlier, non-probability methods don't use a fixed equal chance selection process. They definitely carry a significant risk of skewed, non-representative results. So, why even use them? Well, convenience sampling is used when you simply select data because it's incredibly easy to access, like pulling directly from an internal database you already have open. But judgmental sampling, that's where it gets really interesting. Imagine a seasoned auditor named Perkyamin Kanzua. He's under a massive time constraint auditing the Kanemagat Corporation. He can't just use pure random sampling. He absolutely must selectively handpick the most crucial, high-risk transactions based on his deep professional knowledge. In a scenario like this, expert judgment is way more efficient than a random number generator.
Section 4. The Central Limit Theorem, the magic rule.
This quote right here is the formal definition of the Central Limit Theorem. And let me tell you, it is incredibly powerful. It basically states that no matter what crazy, non-normal shape your underlying population distribution looks like, if you draw a large enough sample, the distribution of your sample mean will magically form an approximately normal distribution, a beautiful, perfectly predictable bell curve. And in the world of statistics, large generally means a sample size, or N, of 30 or more.
Now, when we visualize the math, it is wild to see this transformation in action. With a tiny sample size of just 10, the distribution of sample means is totally scattered and blocky. It's essentially chaos. But watch what happens as we increase our sample size. By the time we hit an N of 50, a solid center starts to form. Pushing it to 100, that classic bell curve is really taking shape. And finally, by the time we reach a sample size of 300, we're left with a wonderfully tight, perfectly predictable normal distribution centered right exactly on the true population mean. It's like magic, but it's math. Let's look at some real data from the Euro-Asia-Africa Equity Index to perfectly illustrate this real-world impact. Look at what happens to our villain, sampling error. With a tiny sample of just 5, our error is almost 0.3%. But as we increase our sample size N up to 1,000, that mean absolute error radically shrinks to practically zero, just 0.009%. You'll probably also notice that stratified sampling continues to give us a slightly lower error than random sampling all the way down the board.
So a super crucial point here is to make sure we distinguish between standard deviation and standard error. They are absolutely not the same thing. Standard deviation describes your data. It measures how spread out your individual data points are from the mean. Standard error, however, is a measure of inference. It measures the actual precision of your estimate. It tells you exactly how much inaccuracy in your sample mean is caused by the very act of sampling itself. And thanks to the Central Limit Theorem, we can calculate this to know precisely how far off our estimates might be.
Section 5. Modern Resampling Techniques, the computer hacks. Sometimes we just can't use standard analytical formulas to find standard error. When that happens, we turn to simulation techniques like bootstrapping and jackknife. Comparing these two methods side by side perfectly cements the difference. In bootstrapping, you repeatedly draw samples from your original data, but, and this is key, you put the data point back into the pool each time. We call that with replacement. Jackknife, on the other hand, selects samples by strategically leaving out exactly one observation at a time, without replacement. Jackknife is fantastic when your main goal is reducing the bias of an estimator.
Let's quickly walk through this clever bootstrapping workaround because it's super cool. Usually we sample from a population, right? But if we don't know what the population actually looks like, the bootstrap method just mimics it by treating our original observed sample as if it were the population. The computer then repeatedly draws random samples from it, again with replacement. We compute the mean of each of those thousands of resamples, and then we just calculate the standard error across all of them. It is such a brilliant way to use raw computational power to establish statistical confidence when traditional formulas completely fail us. And just like that, we've reached the end of our toolkit. We've explored everything from the incredible time-saving power of stratified and cluster sampling to the sheer mathematical magic of the Central Limit Theorem, all the way down to modern resampling hacks like bootstrapping. You now know exactly how to strategically trade time and money for a highly calculated, totally manageable sampling error. So, I want to leave you with a final thought. How will you apply these powerful concepts of estimation and inference out in the real financial world to eliminate bias in your next big data project? Seriously, think about it. Thank you so much for joining me for this explainer. I had a blast, and I look forward to exploring more fascinating topics with you next time. Keep learning and stay focused out there.